All right, so chapter 2 review. We'll just go ahead and get right into it. Luis or Lewis, whatever, however you want to say it, wears an outfit every day that consists of one top, one bottom, and one scarf. Her wardrobe consists of a tan skirt, a pair of black pants, a pair of blue pants, a plaid skirt, 3 t-shirts, 2 silk blouses, 3 button-down shirts, and a set of 4 scarves. How many different outfits can Lewis or Louise put together? Or Lois, I don't know. Anyway, it doesn't matter. So it's going to be a top, a bottom, and a scarf. So if we can figure out how many ways of each, we just simply multiply those values together to get a total. We saw this a little bit at the very end of chapter 1 review. So let's look at the tops. How many options does she have for tops? She has 3 t-shirts. Remember, tops are shirts, t-shirts, and blouse. So 3 t-shirts, 2 blouses, and 3 button-down shirts. So 3, 2, and 3, that's 8 different top options. Now we'll look for bottoms. So bottoms are pants or skirts. So she has one tan skirt, a pair of black pants, that's 2 in total, a pair of blue pants, that's 3 in total, a plaid skirt, that's 4 in total. So it seems she's got 4 different options for bottoms. All right, and then how many options does she have for scarves? Well, it says she has a set of 4 scarves, so she got 4 scarves. So if you multiply them out, you'll have your total. So I'll let you guys do the multiplication. Number 2, there are 13 singers competing in a talent show. How many different ways can the singers appear? So basically, if you think about, I guess the order of the 13 singers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. If there are 13 people, then for the very first singer to go, there are 13 people in total to choose from, right? That's for that very first person. Once that person is gone and they've performed, then there are 12 people remaining to choose from for the second singer to go. And then once the second singer is gone, then there's 11 more people remaining that could go third. So there's 11 to choose from. Once a third person's gone, then there are 10 people remaining to go fourth, and so on and so forth. So you end up ultimately with that all multiplied together, which is the same as 13 factorial. So 13 with an exclamation mark is 13 factorial. What 13 factorial means is basically what you see here. It's starting at 13, multiplying every single number consecutively all the way down to 1. 13 factorial. And you'll see that comes in a lot in this section. So number 3, Joel owns 18 shirts and is selecting the ones he will wear to school next week. How many different ways can Joel choose a group of 5 shirts? Note that he will not wear the same shirt more than once during the week. In this section, we're going to talk a little bit about permutation or combinations. So remember, before I get into this problem, permutation means it's like a combination, but it's a combination in which order matters. Combination in general is when order doesn't matter. So in this problem, it's saying he's choosing a group of 5 shirts. It's not necessarily indicating that it really matters which order he wears the shirts in, as long as he has like these 5 shirts for these next 5 days of school. So it doesn't tell us the order of the shirts matter. So because of that, this is a combination problem instead of a permutation problem. So a combination, as we write, combination NR, N being the total number of ways, R being the specific ones we're choosing. So in this case, this would be the combination of 18, since there are 18 in total, and R being 5 because we're choosing 5. So a combination of 18, choose 5. And we can do that in the calculator. if you remember, and just I'm probably going to show you this one time. I might pull it up again because some people are going to fast forward through the video, but to get the combination, you hit math button. And then from the math key, you arrow over towards probability. And number 2 is permutation, but we're using combination, so we're going to use option 3. We're going to type in 18, choosing 5. So hit enter, and that is 8,568. So 8,568 different combinations of shirt pairings you could wear, which is a lot, but it is what it is. Also, the formula for this, originally, when we did chapter 2, we didn't actually use the calculator. We used the formula. The formula for combination was n factorial over n minus r factorial. So in that case, that would have been 18 factorial over 18 minus 5 factorial, which is, I guess 18 factorial over 13 factorial. But that's neither here nor there. You guys just can use your calculator. That's fine with me on the exam. I'm not too worried about it. So number 4, an experiment has outcomes 1, outcome 2, outcome 3. Probability of outcome 1 and 2 is 0.85. Probability of outcome 1 and 3 is 0.6. What is the probability of outcome 2? So here's what you need to remember. Probability always adds up to 1. So outcome 1 plus outcome 2 plus outcome 3 is going to be 1. Now what it's doing here is it's pairing some up. Outcome 1 and 2 together make 0.85. So if I know that outcome 1 and outcome 2 is 0.85, then I can figure out what is left over must be outcome 3, and that has to equal 1. So if outcome 1 and 2 is 0.85, then outcome 3 must be 0.15. And also you can do 1 minus 0.85 if you couldn't do that in your head, but just take the difference, and it turns out outcome 3 must be 0.15, just based on that information that I was just looking at here. That the first two together is 0.85, so that third outcome, outcome 3, must be what's left over to 1, which is 0.15. Now, the second one here, probability of 1 and 3, so I'm going to change the order here a little bit, but probability of 1 and 3 is 0.6. So if together 1 and 3 make 0.6, that means outcome 2 has to be what's left over to get to 1. So that must mean outcome 2 is 0.4, because 0.6 plus 0.4 would equal 1. So outcome 2 must be 0.4. Now the question was asking what is the probability of outcome 2, so I went ahead, that's it there. So I'm not even going to bother doing anything more to this problem. It's pretty simple, so try not to overthink it. Number 5 and 6 are relatively the same. I'm going to let you kind of do those. Number 7. So number 7, we have a 6-sided die, 3 odd sides, 3 even sides. It's weighted such a fashion that the probabilities of all the odds are the same, all the even sides are the same. The key sentence here, the probability of obtaining a given odd side is twice that of giving an even side. So I have 6 sides altogether, right? A 6-sided die. We have 3 of the sides even and 3 of the sides odd. Now, I know probability always adds up to 1, but the thing is, I don't necessarily know what the probability of each side is, but I kind of do. I know that odd sides are twice that of an even side. Now, I don't know what an even side is. I don't know how much an even side weighs, but I'm going to call them X because they all weigh the same, so every even side is going to be weighted, let's say X, whatever X is supposed to be. And an odd side, key here is odd side is twice an even side. So if an even is X, then an odd side is twice X, or 2X. So every odd side will be weighted as 2X. So now if all of these add up to 1, I can simply combine all these like terms, x plus x plus x plus 2x plus 2x plus 2x. That all adds up to 9x equal to 1. And so now if I want to know what x is, I know I can just divide by 9, and I can see that x is equal to 1/9. But remember, x was the even sides weight. So even sides are weighted, 1/9. But the question's asking what's the probability of an odd side. If an odd side is twice that of an even, then an odd side will be 2/9. That's twice 1/9, right? So 2/9 is the final answer for number 8 or number 7. That was weird. So all of these are the same. 8 and 9 are pretty much the same thing. Just be aware that in number 9, an odd side is 3 times that of an even. So if an even side is x, an odd side will be 3x. But 8 and 9 work out essentially the same way. Okay. Number 10, 11, 12, 13, 14, and 15 are all done on the calculator. So if you pull up your calculator, remember, I already showed you where to get it before, but just to remind you, if you hit the math button and then arrow over to the probability tab, we're going to do permutation here. I think that's what the first few are. So permutation. What was that first one that we're doing? Permutation 7 choosing 2. So simply going to type in 7, choosing 2, and hit enter and solve it, and we get 42. So the calculator will do all of those. I'll let you guys handle that. You can do it without a calculator, but I mean, why would you? You know what I'm saying? Number 16. 18 letters are available to be used to form 3-letter words. If no letter can be repeated, how many such words can be formed? So here's the thing. 3-letter words. Again, this is about permutation versus combination. So permutation, again, to remind you, permutation was where order matters. Combination is where order doesn't matter. So you have to tell me, if you're choosing letters, 3 letters to make a 3-letter word, obviously it's probably not going to make sense, but if you're choosing letters to make up this word, will the letters matter, or the order of the letters matter? Well, yeah, because if you choose the letters, I don't know, we'll just make it simple, A, B, and C. I know it's not necessarily a word, but we'll pretend it is. That word, quote unquote, would be different than B, A, C. Okay. It's the same letters, but it's a completely different word. So because of that, order of the letters matter. And since order matters, that means this is going to be a permutation. So permutation of n choose r. Remember, n is the total number in general, which there are 18 letters available, so there's 18 here. And r is the number we're using, so we're using 3 letters. So permutation of 18 choosing 3, whatever that comes out to be will be our answer. So again, I can let you just use the calculator to get that number. Number 17, a sales representative handles 12 different products, and how many different ways can these items be listed vertically on a computer? So this is very similar to the singing competition or whatever that question was earlier. I think number 3, or was it on chapter? I don't remember what it was. But anyway, so there are 12 different products. 7, 8, 9, 10, 11, 12. So the first product that you choose, there's 12 options. So you can choose any one of 12. So there's 12 possibilities for option 1. Once you've picked one of them, then for the second slot, there's only 11 remaining. Once you've picked 2, then for the third lot, there's only 10 remaining, and so on and so forth. So what this comes out to be is simply whatever 12 factorial is. 12 times 11 times 9 times 10 times 9 times 8 times 7 times 6 times 5, so on and so forth. That number is the number of different ways in total. Number 18, there are 7 cars parked in a line out along the side of the street in front of your house. How many different arrangements are possible? So this is just the same as the last problem. This is 7 factorial because there's 7 options for the first car to be parked. And then once the first car is parked, there are 6 other cars to choose from for the second slot. Once the second slot's filled, then there are 5 remaining cars to choose from. And then so on and so forth again. So 7 factorial, whatever that ends up being. This is really weirding me out, by the way. Okay. Number 19. How many different combinations of 17 items can be taken 7 at a time? So it tells us combination, 17 total items, choosing 7 at a time. So combination of 17 choosing 7. I'll let you guys kind of do that in the calculator. I'm just hoping that this goes away. Number 20. Consider the set 1, 2, 3, all the way to 11. How many subsets are there with exactly 2 elements? Now, here's the thing. Again, it's about combination versus permutation. So if you're going to choose a subset here, any 2 elements in that set. So an example, a subset could be the elements 1 and 2. That could be a subset. It's got 2 elements. It's elements from that set. So there's a subset. The subset 2, 1 is exactly the same set. So in this case, the order of my numbers does not matter because this set is the same as that regardless. Order doesn't matter in the set. It's the same 2 elements either way. So since order does not matter in this becomes a combination problem instead of a permutation problem. And it's a combination of 11 because that's how many there are to choose from. And then choosing 2 because we're picking 2 elements. So that will tell us, the combination of 11 choosing 2 will tell us how many different subsets we could make. Number 21, a group of 7 boys are playing basketball. And how many different ways can they make different teams if 4 boys are to be on one team and 3 are to be in the other? So it does not matter the order I choose my teammates. If I choose Ralph, Lenny, and Ben, it doesn't matter if I chose Ralph first and Ben third, or if I chose Ben first and Ralph second. It doesn't matter. It's the same people that make up my team. So the order that I pick my teammates doesn't matter if I still have the same teammates. So this will be a combination, and there's 7 in total. Remember, N is the number in total. R is the number we're choosing, and we're choosing 4. So combination of 7 choosing 4 will tell me the number of ways I can choose a team of 4. And by default, that also sets the other team of 3. So we don't have to worry too much about them. This will be our answer, whatever that comes out to be. Number 22. A committee consists of 6 men and 7 women. How many subcommittees can be formed, which contain 3 men and 3 women? So again, the order that I choose my people doesn't matter. If I choose Ralph, Ben, and Lenny, it doesn't matter. Again, if I chose Ralph first, it's just the same 3 men would be in the same committee regardless of what order I selected them in. So again, we're going to do it's a combination. So we're going to choose the guys first. So combination, there are 6 men to choose from, and I'm choosing 3 for my committee. So that's combination, 6 to choose from, picking 3 of them. And is the key word here. And means we're going to multiply this with the combination of 3 women. So for my women, there are 7 to choose from, and I'm choosing 3. So if I multiply those combinations together, I have my total number of subcommittee possibilities. Number 23, a jar contains 8 marbles and 8 red marbles and 3 blue marbles. 1 marble is selected at random. What is the probability that it is red? So we're only choosing 1 marble here, so I don't have to worry about combinations because if I'm only picking 1, then what is my combination exactly? So just think of it like this. It's pretty simple. Sometimes people tend to overthink this. There are 8 red, 1, 2, 3, 4, 5, 6, 7, 8, and there are 3 blue, 1, 2, 3. So that makes my jar full of 11 marbles. And I'm picking one of them. Okay? There's 11 in total in there. And I'm going to pick one. What's the probability that it's red? Well, 8 out of those 11 are red. So 8 out of 11 are red. That's my probability. It is technically a combination problem. You can think of it. It's a combination of choosing red. There are 8 to choose from. You're choosing 1. Out of the combination total, there's 11 to choose from, and you're choosing 1. So it is technically combination, but regardless, it's still going to be 8 over 11. So don't overthink that. You might hurt yourself if you do. Number 24, while playing a popular board game, a player needs to roll a sum of 7 in order to buy a certain property. If 2 fair dice are rolled, what's the probability the player gets a sum of 7 so she can buy the property? So this comes in handy because you guys play Monopoly sometimes, right? Anyway, let me illustrate this question with a table. I should really make this more of a square. But we'll put, the results of die 1 on top. So it could be a 1, a 2, a 3, a 4, a 5, or a 6 that I roll. And the second die on the side, I can roll 1, 2, 3, 4, 5, or 6 on that side. So what I'm going to do here is just kind of show you all the possibilities that I could roll. If I roll a 1 and a 1, that totals up to 2. If I roll a 1 and a 2, that totals up to 3. If I roll a 1 and a 3, that total is 4. If I roll a 1 and a 4, that total is 5. A 1 and a 5, that total is 6. A 1 and a 6, that total is 7. So I'm just going to fill this all out. This would be a 3. This would be 4. 2 and a 2 would be a 4. 2 and a 3 would be a 5. I'm just going to fill this all out just so I can see all the different sums. Oops. 3 and a 3 makes a 6, not an 8. So that'd be 6, 7, 8, 9. This will be a 5, a 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, 12. So the red numbers show me my sums if I roll those 2 specific die. So if you count them all up, that's 6 times 6. That's 36 ways in total I could have my dies land. Now, how many of those 36 roll a sum of 7? We'll count them. There's a 1, 2, 3, 4, 5, 6 ways I could roll a 7. 6 out of the 36 in total, which is my answer, but I can reduce that to 1/6 if I want to. So a 1 in 6 chance she rolls a 7. All right, number 25. There are 5 nickels, 8 dimes in a bag. An experiment consists of selecting 3 coins simultaneously and at random, and noting the value of the coin selected. Find the probability that the value is 25 cents. Now, you're choosing 3 coins, and the first thing you need to remember is that when you choose 3 coins and the total is 25 cents, there is only one possible way you could have that happen. You choose 3 coins and the total is 25 cents. That means you've picked 2 dimes and 1 nickel. There's no other combination of coins that would give you 25 cents and it being exactly 3 coins. So you are choosing 2 dimes and 1 nickel. Okay. And we're looking for probability. So the first thing we want to do with noting probability is how many ways are there in total? So just like the last problem that had the die, there were 36 ways in total to roll that die. But in this case, I have 13 coins, and I'm choosing 3 of them. So the total number of ways will be the combination of 13 choosing 3. So whatever the combination of 13 choosing 3 is, that number is my denominator. That is the total number of ways I can select 3 coins out of 13 that are in this bag. But my numerator will be my specific case of 2 dimes and 1 nickel, the values that get me 25 cents. So the combination of choosing 2 dimes, there's 8 dimes to choose from, and I am selecting exactly 2 of them in this situation. And again means multiply. So multiply that with choosing 1 nickel. So think about the combination of nickels. There are 5 nickels to choose from, and I am choosing exactly 1 of them. So that right there, whatever that total is, will be the numerator of my probability. So multiply those together, you'll have your numerator, and then the combination of 13 choosing 3 will be your denominator. And if you can reduce that or simplify that fraction, that's great. You can even leave it as a decimal, but I think on the test, the multiple choice answer probably is in a fraction format. So just something to keep in mind. Number 26, a box contains 5 red, 7 white, 5 blue marbles. If 9 marbles are selected at random, what is the probability of that exactly 3 are red? So let me create a little more space here. All right. This is the longer problem, but it's not necessarily a harder problem. You just have to think about all the different ways to choose exactly 3 red. It's kind of like the ones where we talked about earlier in previous tests when we had we were fishing and we had, fish and they weighed a certain amount, or we picked money and then we counted up how much each bill was worth, from like chapter 4, I think. So this is a very introduction part of chapter 4, this question, but it's on chapter 2. So the first thing I want to point out is, again, just like the last problem, the one before, I want to know how many ways there are in total. So there are how many marbles? 5, 7, and 5. That is 17 marbles. And I'm going to be choosing 9 of them. So the combination of 17 choosing 9 will be my denominator value, because that'll tell me how many ways in total I can choose 9 marbles out of the 17 that are in that bag. So whatever that number is, that'll be my denominator. It should be a pretty big number, if I remember correctly. But now my numerator number comes from exactly 3 red. However, the thing with this is there's a lot of different ways you can pick 3 red marbles. So you could choose 3 red marbles, and the next 6, because we're choosing 9 in total, the next 6 marbles could be white. So that's 9 marbles, exactly 3 red, and the other 6 being white. There's another way we could choose 3 red, though. We could choose 3 red. I could choose, out of the 6 remaining, 5 of them could be white, 1 of them could be blue. That's 9 marbles selected, but again, exactly 3 of them are red. So I'm doing this for every possibility of red that I can think of. So I can have 3 red, I can have 4 white, and 2 blue. That's 9 marbles, exactly 3 red. I can have 3 red, 3 white, 3 blue. I could have 3 red, 2 white, 4 blue, and I can have 3 red, 1 white, and 5 blue. Now I can't do any other option because I can't do all 6 blue because I don't have 6 blue marbles. It says I have 5 blue marbles, so I can't do anything more. But these are all the different ways I can choose exactly 3 red marbles with variants of the others. So what I have to do is I have to find out all those probabilities and add them up. So for each of these, it's just simple combinations. So the first one would be a combination of 3 reds. So there's 5 red to choose from, and you're picking 3 of them, times the combination of 6 white. So there are 7 white to choose from, and you're going to pick 6 of them. So that would be your total for that first possibility. The next one would be the combination of 5 choosing 3, because again, there's 5 reds and we're choosing 3 of them, times the combination of 7 choosing 5. This is because there are 7 whites and I'm choosing 5 of them. And then blues as well, combination of 5 choosing 1, because there are 5 blues and I'm choosing 1. So this is going to have a few more as well. This will be 5 choosing 3 for the 3 reds, combination of 7 choosing 4 for the 4 whites, and the combination of 5 choosing 2 for the 2 blue. Combination of 5 choosing 3, combination of 7 choosing 3 for the whites, and combination of 5 choosing 3 for the blues, combination of 5 choosing 3 for the reds, combination of 7 choosing 2 for the whites, combination of 5 choosing 4 for the blue, and then one more. Combination of 5 choosing 3 for the red, combination of 7 choosing 1 for the white, and combination of 5 choosing 5 for the blue. So whatever these end up being, if you add them all up together, that will be your numerator value. And it's not even close to as big as the denominator value, which was 17 choosing 9 we found earlier. So it is a bit of a handful. It's not necessarily difficult, I don't think, because the most difficult part in my mind is coming up with all these scenarios, but these scenarios aren't necessarily difficult to comprehend. Combinations are pretty straightforward. I feel like we've practiced those a lot. It's just a lot. There's 6 different ways here, and there's a lot of numbers to multiply together, but it's just a matter of putting in the calculator. I don't think it's time consuming maybe, but it's not too difficult, I don't think. Number 27, there are 5 black mice, 5 white mice available for an experiment, which requires 6 mice. It's supposed to say 6. Oops. Okay, that says 6 mice. If a random selection of 6 mice is made from the set of 10, was the probability that 3 black and 3 white mice are selected. So again, probability, let's focus on our denominator. Our denominator, I have 10 mice to choose from, and I'm going to be choosing 6 for my experiment. So the combination of 10 choosing 6 makes my denominator value. Now for my numerator, I have to speak specifically about the problem, 3 black and 3 white. So if I'm going to have 3 black mice and 3 white mice, then I'm going to have the combination. For black, there are 5 black mice, and I'll be choosing 3 of them, times the combination of there are 5 white mice, and I'll be choosing 3 of them. So those combinations multiplied together will be the combinations of exactly 3 black and 3 white. So remember, these problems are all very similar. The denominator, you talk about a total that you have that you're selecting from and the number you're selecting in general. So there are 10 mice, and I have to choose 6 of them. So that 10 choosing 6 tells me how many ways I can choose 6 mice out of those 10. But then more specifically, you get to the numerator. The numerator speaks about your particular situation. So I'm looking for 3 black and 3 white. So I specifically get into those combinations from black and white. So there are 5 black, and I'm selecting 3 of them. So there's the combination for my black mice. There are 5 white mice, and I'm choosing 3 of them. So my combination for white mice. Multiply together because it's and 3 black and 3 white. And I believe, once you get that number will be your numerator, and you'll have your fraction or your probability. Number 28, a bucket contains 5 orange tennis balls and 5 yellow tennis balls. 5 balls are selected simultaneously at random. What is the probability that at least one is orange and at least one is yellow? So basically, the question here is simple. This is only going to refer to basically any pairing that has more than one color, right? At least one orange and one yellow. It's referring to every combination of colors that has a mixture. So first thing I want to do is, again, my denominator. The combination of how many balls are there to choose from. There are 10 to choose from. And how many am I choosing specifically? I'm choosing 5. So the combination of 10 choosing 5 is my total possibilities. Now, I believe that number is 252. I'm going to go ahead and work that out. 10 choosing 5 is 252. I'm going to check that in my calculator just to be safe. But the combination of 10 choosing 5. I don't know if I said that before, but there we go. 252. Yeah. All right. So the probability on top is all the ones that have at least one orange and one yellow. But what's easier to think about is how many possibilities are there where there's not a mixture? How many different possibilities of those are there where it's all one color? Well, the only possibilities, if I'm choosing 5 balls, they could all 5 be orange, And that would be all one color. That wouldn't have at least one yellow with it. So how many ways could I choose all 5 orange? Well, there are 5 orange in total, and I'm choosing all 5 of them. That's only one possibility. There's only one way I could choose all 5 of them to be orange. And then also, how many ways are there for all 5 of them to be yellow? It's the exact same thing. There are 5 yellow, and I'm choosing all 5 of them exactly, and that's another. And those are the only 2 ways in which I don't get a mixture of colors. Those are the only ways where all 5 balls are the same color. So if there's only 2 ways in total where none of the balls or basically there's no mixture, there's no different colors in them, every other remaining possibility has at least one of each color. So if there's only 2 out of 252 that do not have a mixture, then that means 250 out of 252 have at least some mixture. And number 29, if 5 qualified individuals, including a wife and husband, apply for 3 vacant sales positions, if people are hired at random, what is the probability that both the husband and wife are hired? What is the probability that one is hired and the other is not? So again, let's figure out how many ways there are in total in this. So there are 5 individuals competing for this job, and exactly 3 of them are going to get it. So the combination of 5 choosing 3 will be my total number of combinations for these jobs. And that number is 10. So there are 10 different ways these people could be given jobs or handed out jobs. So what's easiest for me? Well, let's find out the probability that both the husband and wife are hired. Well, both husband and wife is a combination of how many jobs there are available. There are 3 jobs available, and both being hired means, 2 of them, or choosing both of them to fill 2 of 3 out of those 3 jobs. So the combination of 3 choosing 2, 3 jobs in total, both of them are getting hired. That is a total of 3. So there's 3 out of 10 ways that they both get hired. Now the other question is how many ways do either one of them get hired? But again, this is easier found, like the last problem, number 28, if I figure out the ways in which none of them are hired. So if there are 3 job positions and neither of them get hired, well, that's only one possible way of happening. Think about it. There are 5 people, right? Let's just say, I'll draw little stick figures because why not? We've made it this far into the video. I can have a little fun drawing stick figures. So great. There's these 5 people. Okay, all gender neutral, so don't get mad at me. All right. Let's say this is the husband and the wife. All right, these 3 people get hired for the job. And then, well, the only 2 people that don't get hired are the husband and the wife. So that's the only possibility of that they could be left out. The only way they get both not get the job is if all 3 of the other people get the job and both of them do not. That's the only way it happens. So only 1 out of the 10 ways are neither of them getting hired. Okay. Which means if that's 3 and that's 1, that's 4 ways accounted for already. Then the other 6 out of 10 ways must mean either 1 or the other of them gets hired. 6 out of 10. 3 out of 10, both. 1 out of 10, neither. 6 out of 10, one of them gets hired. And that's going to be it for chapter 2. Sorry again for it to be so long, but I try to be thorough. Okay. We'll see you in chapter 3.